Welcome back to Science for Skeptics. This is going to be a little bit different this time. I know I promised empirical studies and we've been doing those, but now I'd like to take a little bit of a time out from that and talk about the math we've discovered and what it can tell us. If you've been following along with this series, then you've seen this equation before. This is my law of relative density. I have presented this before, but I originally was putting a W here for weight, but that was very confusing. So we're going to change weight out. We're going to replace that word with the word net force. This is the net force that we see acting on an object suspended in a medium. What does net force mean? Well, for those of you in the relative density camp, the net force means whether the object is going to rise or sink, and how hard the object is going to rise or sink. If we get a downward pointing force here acting on the object, then that means we are going to observe the object accelerating downward. It's going to sink in the medium. But on the other hand, we might see an upward pointing force, like a helium balloon or bubbles bubbling up through water. And in that case, if we have an upward pointing force, that indicates the object will rise and float. Okay? For those of you in the gravity camp, what does net force mean? Net force means we are including both gravity and buoyancy together. They've been added together to give us a net force as a vector, with the same results that I just described. Let me emphasize that this force we're looking at here is not only the direction, but it is also the magnitude of the force. If we put a scale in there, we can measure how hard the object is pushing down on the scale. Or if it's like a helium balloon or something that's rising, we can rig up a little scale or something to measure how hard the helium balloon is trying to lift. And that will be a number that we can put in there to go together with our direction to give us the force vector. So what I'd like to do is read back this mathematical sentence and translate it back into good old plain speak, plain English. We say we like to use the language of mathematics to describe science because it is so precise. Instead of arguing and making hours and hours of YouTube videos trying to describe what we mean by relative density, if we can write it mathematically, we can be extremely precise and convey those ideas to anyone who can translate that mathematics. So I know many of us are not native speakers of the mathematical language, so let me just go through and read this back and see what is this saying. Let's start with this force here. I've said before that I want it to be a vector. Now that is because all forces in general are described as vectors because they have both magnitude and direction. We say how hard you push, and we also need to say which direction do you push. Now for our cases, let's just talk about weights on scales and balloons pulling up. So weights and buoyancies will always point either up or down. The weight will point down, the buoyancy will point up. So we could say we don't really need the direction, but in order to be precise in the language of mathematics, we're going to include that direction. Now there's many reasons for why we need to do that, but let's just stick with we want to be precise. We want to say exactly what does this effect do, and we need a way now to describe in mathematics what does it mean to say down. Now you've heard that from the gravity crowd over and over and you're sick to death of it. What does down mean? You think it's enough to just say down, but we need to translate that into mathematics so that we can be completely precise. Let's do that right now. To describe a vector, we're going to need an axis. So I'll just draw a good old axis just like we've done in math class do a nice two-dimensional axis. Let's keep it simple, go two-dimensional. This is the way I always do them. X will go to the right and Y will point up. So what does it mean now to point down? Down means this. We all know what down means, but now we can say mathematically that down is the opposite of Y. Y is defined as up, so down is minus Y. And we can write it mathematically. Let's write down as a vector mathematically. Down equals, and I'll use a square bracket, down is how much X. We'll just put two terms into square brackets, and that will be our vector. This will be how much is the X, this will be how much is the Y. So how much of down is in the X direction? None, 0. How much of down is pointing in the Y direction? Y points in the opposite from down. So we have minus 1. So we put 0, minus 1 in square brackets. Now we have defined that is down. So maybe throw that one at the next time the gravity folks want to annoy you and ask you what is down. Just tell them the vector 0, minus 1. Okay, and see how far that gets you. I don't know, it's worth a shot. Anyway, that covers force and why force is a vector and how we write vectors. So we'll be looking for a 0 in the X for our weights, and for something heavy, we want a down, and so that'll be a negative number in the Y column. Something floating up would be a positive number in the Y column. Either way, we're going to look for a 0 in the X column. So that covers the force. Next up, let's put in this K. Let's put in the K. Give me a vector here. Give me an axis. Same old axis. We'll put the X on the right. We'll put the Y pointing up. And what is K now? K, I've said this before, I want K to be a downward vector with a magnitude of 1. So this is K. It's a vector, and it has the value 0, minus 1, and it has units of grams force per grams of mass. Now, that's a funny little unit, but usually you're going to hear that unit described as 1G. If you look at your accelerometer will read out in G's. 1G is what your accelerometer reads when it's just sitting there on your desk, right? That is the units it is trying to tell you. 1 gram of force per 1 gram of mass, that's 1G. Okay, so let's put that in for our K. And I didn't tell you where I got this from, but I think we'll see in this example when I fill in all the numbers that is going to work out exactly the way we want to. Next up, we have the parentheses here, and that is our relative density. That's the workhorse of this whole equation. We want to compare the density of the object to the density of the medium that it's in, and the minus sign is doing the hard work of telling us if these two values are equal, we're going to get 0. And that means we're going to get 0 force, and the object will just hover at balance, at equilibrium. It will be at equilibrium when it matches. That's the magic words for relative density. We're going to take the relative density, and if that's 0, the object is at equilibrium. We'll have no net force acting on it. And that's how we say that mathematically with this subtraction. Okay, what else can we say with that subtraction? Well, if the density of the object is greater than the density of the medium, this will be a positive number after we do the subtraction, and that will result in a positive number multiplied times K, which will give us a force pointing in the same direction as K, which is what we want. We want a rock in water to give us a downward force, and we'll get down out of this equation by putting K into there. All right, that's that. The last term here is the volume, and the function of putting volume on here says that the larger the object is, the more it's going to weigh. Or if it's a buoyant object like a helium balloon, the larger the balloon, the harder it can lift, the more weight it can lift up off the ground. So that's why that is on here. So this is not a cause necessarily, but this is a mathematical description of what we want to happen. Okay, I think the best way to really understand an equation like this is to go ahead and plug in some real world numbers and see what it does. How does it work? How do we apply this? Now, it so happens I did this back in an earlier video. I weighed a rock in some water, and we can plug in those numbers and see what we should get. K was 0, -1 grams of force per gram of mass. And what was the density of our rock? We measured in the kitchen 2.62 grams of mass per milliliter of rock. And the density of water we can measure as 1 gram of mass per milliliter of water. And then the volume, we'll put the volume of the rock on here, and we measured that as 21 milliliters. Okay, so how do we get the force? Let's multiply this out and see what we get. First thing we do is the parentheses. We always, do the parentheses first. So let's go ahead and do that. We're going to bring down the K, 0, -1 grams of force per grams of mass. And let's do the parentheses. 2.62 minus 1 is 1.62 grams of mass per milliliter. These have the same units. Watch out for that when you do a subtraction. It must have the same units. And then we'll bring down the 21 milliliter volume for the rock. Okay, now what do we do? Let's go ahead and clobber those units next. I'm tired of writing the units, so let's do them. Here I have divided by milliliters, and this is times milliliters. So that's milliliters divided by milliliters. That cancels out. And here I have grams of mass divided by grams of mass. That will cancel as well. So now I can get rid of those units except for this one that's left, just grams of force. So I'll keep those. All right, what shall I do next? Let's multiply the 1.62 times the 21. So we'll bring down the K, 0, -1, and our units, grams of force. So I'll keep that. And then we'll multiply times. We multiply this out, and we get 34.02. Okay. Multiplying that out, that's what I got, 34.02. And now we get to the sticky bit, the bit where we have to multiply a vector times a scalar. A scalar is what you call it when the number's not directional. It's just a number. So we have to multiply that out. The way we do it is we multiply each term. So the first term of the answer will be the first term times the thing. And 0 times anything is just 0. So that's easy. Now, for the second term, we multiply the second term times the thing. And so we write minus 34.02. And that is in units of grams of force. And that's the force acting on our rock is negative 34 grams of force. Let's take that over to our axis diagram here. Let's do it in blue. So we'll draw a little axis. Here's our y-axis. Here's our x-axis. Put the arrows so that you're clear. Want to be precise. Now, what did we get? We got a force downward with a magnitude of about 34, so 34.02. I'll put all the digits in there. We're beyond our sig figs, right? But I'll put them. Okay, we got 34.02 grams of force. I'll put that there too. Grams of force as measured. What did we measure on our scale, right? We measured this on the scale. What did we get? If you review and you remember, we got 34 grams of force is what we measured, and that works, right? This works. That is why the equation is written that way. So that is our law of relative density, and hopefully this example has shown the usefulness of this expression, how we can use it to estimate what the weight or buoyancy of an object will be in different mediums, how much it's going to weigh, how much it's going to be buoyant, how much can you load into your boat before it sinks. We can use this expression to answer that question. Now, more important than that though, I wanted to express how this very concise mathematical statement has conveyed all of our observations in a very small little statement. We don't need hours and hours of discussions and descriptions of these observations if we can boil it down to a very simple mathematical statement like this, and we can learn to read that language. And that is why scientists like to work in the language of mathematics. Hopefully we can move forward with this expression and start to pick apart the different components and what they mean in a more physical sense. And hopefully that'll be next time.